All right, so in the previous video, we left off with this matrix times v is equal to the 0 vector. And now we need to go through and do row operations to reduce this matrix down as far as possible. And most graphing calculators cannot handle complex numbers and matrices, so we almost always have to do these by hand. So for the first one, we'll go through, and we want to convert the imaginary number to a real number. So it's always best to multiply by a conjugate to do so. But before we do any of that, we notice that we have a factor of 3 in every single row. So let's go through and first multiply by 1/3 for each one of these rows. And that'll just downsize all of our coefficients. So that's going to leave us with a negative I and a 1, a negative 1, and a negative I for our matrix. And again, what we'll do is now multiply through by the conjugate to convert the imaginary number into a real number. So the conjugate of negative I is just I, so it's I times R1, put the result into row 1. So when we do that multiplication, we are going to get a negative I squared, and we get an I, and negative 1, and a negative I down here. And of course, I squared is equal to negative 1. So that's actually going to be a negative of a negative 1, I, negative 1, and negative I. And then when we go through and simplify that down, we end up with the matrix that is 1, I, negative 1, and negative I. And it should be pretty obvious to us that we can just add together those two rows to get 0 for our second row, since they're exact opposites of each other. So when we add those two rows together, we end up with the matrix 1, I, and 0, 0. And again, we have to always have a row of zeros when we do these operations to know that we actually have the correct eigenvector that we're finding. All right, next thing to do is now bring back in our v, which again is component-wise v1 and v2, and that is equal to the 0 vector 0, 0. The next step is now to multiply out that top row, and it says that 1 times v1 plus I times v2 is equal to 0. So it says that v1 is just equal to negative I times v2. So when we build v back again, we're going to have a negative I v2 and a v2. Factoring out the v2 gives us the eigenvector of negative I and 1. And again, this corresponds to lambda is equal to negative 1 plus 3i. So now that we found our eigenvector corresponding to our eigenvalue, we need to go through now and find our solution. And remember, our solution was y of t was e to the lambda t times eigenvector v. So that's going to be e to the value negative 1 plus 3i times t times our eigenvector negative I and 1. And now we're back in the location where we have to use complex exponentials, and of course we need to use Euler's formula for this. Before we do that though, we can simplify down our exponential a little bit. That's e to the negative t times e to the 3i t times negative I and 1. So on the next step of the problem, we'll go through and now express this back into sines and cosines and get our solutions.